And this, let's say, this data can be used to utilize this hardware. Of course, your hardware can support other 128 data compositions. What else? Also, we can use a part of the SAMD hardware. So in this picture, you see the half of the hardware used to process 64-bit data. And similarly, we can process the 30-bit data by using the quarter of this hardware. This is not something new. Yeah, you have seen also in the previous presentation. One of the most recent and known example is AVX 512 architecture, which is used in Xeon Phi and use this kind of register partitioning. So we have some observations. You have seen that these units and the register files, which provides the operands for these units, are getting wider and wider. And if you don't use all the lanes of the hardware, what we do usually, either we ignore the results of some lanes, masking, for example, or we do the hardware tricks. We disable some units through the clock or power gating. But both has a performance and/or energy cost. So what we propose here, can we introduce more SAMD heterogeneity in the processor and push the problem to the compiler side and tackle the problem in the compiler? So the kind of architecture we focus is VLIW architecture, as I mentioned. So in this kind of architecture, you have multiple units that you can use for execution of multiple operations in parallel. And the type of heterogeneity we are talking here is having a VLIW with multiple native SAMD bits. For example, this figures resembles a VLIW data byte where you can have a 128-bit SAMD unit with register files and also 32-bit SAMD unit with register files. So what kind of heterogeneous SAMD or multiple bit SAMD we can get from this example architecture? 128-bit add operation on function unit 1 in parallel with the 32-bit add operation on other function unit 2. And similarly, we can also use the half of the function unit 1 for 64-bit addition in parallel with the add operation on 32-bit unit. And similarly, we can also get this instruction bundle, which is add operation, 32-bit add operation. So in this talk, we will talk about the challenges of first the mixed width vector code generation and also static scheduling in LLVM for this kind of VLIW architectures. So let's start with the first part. So this is the target VLIW architecture we use. Yeah, it has multiple issue slots coupled with the register files. So what we have here, integer arithmetic unit. At the bottom, we have two 64-bit load store units, and we have a compare and move unit. And what's important here and relevant to us for this talk is these two units. So SAU is a 32-bit vector unit, and VAU is a 128-bit vector unit. And SAU is fed by an integer data from the IRF, which is 32-bit, and it's fed by floating point data from SLF, which is 32-bit. And VAU is fed by the data from the VRF, which is 128 bits. So this I already said. What about the compiler? The original compiler I was using was only supporting 128 and 64-bit code generation for the VAU unit, which means that we had some legal types already supported. But what about the 32-bit types? They were promoted to the longer types before the actual vector computation on VAU. So what we did as a contribution, we implemented 32-bit vector code generation in the backend for the SAE units. So let's look a quick look to the how the mixed weight vector code looks like. So this is a simple IR and IR code. So what's important here? We have an operation which uses of 4 by 8 type of data, and another operation which uses 64-bit data, and these operations are independent. So what we get out of the compiler is the following assembly code. And I would like to take your attention on this line, which shows that we have 64-bit vector computation on VLIW unit in parallel with the 32-bit computation on SAU, vector computation on SAU. So what we did to implement this, just very briefly, what you do first, the type legalization, we legalized this, we added these types, 3 vector types as a legal type. What we did next, register class association, we say, okay, which class available for which data, and SRF was available for the floating point vector type, and IRF for the integer type. And also we can say these 32-bit data in quarter of VRF. So the next important thing is adding the support for instruction selection, which is operation lowering. So we added records in the backend to match the IR operation with the machine instructions. And this is done for the natively supported operation in the hardware. But for the rest, what we did, there are options that you can do. You can do the custom lowering. You can expand it to the scalar operation, or you can promote it to the longer operation. And more details about the implementation is already presented in FOSDEM 2015. So, what we have seen in previous slides is about the adding backend, adding support in the backend, and we do the most of the things in table gen files. But when you add such features in the backend, you also think the interaction of what you add in the backend with the rest of the LLVM flow. And regarding vectorization, what we have in the middle end, if you go to the more target independent part, we have some passes for vectorization that you know. And these passes uses checks first, does some legality check and checks for the profitability before doing the actual vectorization. And these passes, they use a cost model to decide if this is a profitable vectorization or not. So if we take an example of loop vectorize, it's also use a cost model, and in this cost model, there are two things decided. Let's say two most important things or relevant things to this talk. One of them is the vectorization factor, where you select the optimum vectorization factor, and the second one is the unroll factor, because we are targeting a VLIW architecture and we would like to utilize the old issue slots. And when we decide this in the cost model, what we use actually, we use data from the target, and we use a API which interface the target with the rest of the flow, which is target transform info. And so for select vectorization factor, we use the get register bit fit information with the get number of registers. These are for the vector, of course. And for the unroll factor, we check the number of registers we have in the hardware just to see the impact of the unrolling on the register pressure, that we don't lead to register spills. So let's look at the TTI of Shave. So the function get number of registers. If it is a vector, it's 32. But if you remember, we had 32 by 128 vector register files. But we also had SRF and IRF, which were 32 bits, and they are also vector register files. But they are not typed here. This is not a part of TTI. what else? We have get register bit width. For vector, it's at 128. But again, we had other two register files which were 32 bit. So let's look at the. This is the x86. This is also the most known backend. And what is the difference from the previous one? Is you have more subtitles here. So some lessons taking and discussion points. So TTI reports only one vector width, as I showed already. So what if TTI reports a set of vector width? Then this can already helps for the optimization for mixed width vector code generation. This is the first lesson we took. And the second one is, even though we have a compiler backend support, still LLVM places the 32-bit data in 32-bit registers and the larger ones in 128-bit vector registers. So there is a strong affinity between a vector type and the register class. So what if the vector type could be associated with a set of register files, but with a strong affinity to one register class? This could allow us moving the operation on the shorter vector type to a longer register class. If in the case of especially register and function unit pressure. And it's also a very valid statement if you are working for the VLIWs, where you can have a identical operation in different issue slots. So this ends my talk, and I will give it stage to Pierre-Andre, so he will talk about static scheduling.
Thank you. Thanks for coming. I'm going to talk about how to approach static scheduling for VLIW architectures such as Shave that Erkan presented. So VLIW processors are usually quite different from, for example, CPUs, and so there are different things you should optimize for, and there are some kind of financial pitfalls you should know about and that you should avoid. So let's start with what to optimize with. As we've seen before, Shave has quite a lot of functional units. So here you can see this 8 units you can use. So the most obvious thing you want to do is to maximize the instruction level parallelism by keeping all these units busy. And two good ways to do this is software pipelining, as you've probably seen the talk this morning about software pipelining for Shave. And another quite good way to do this is to do loop unrolling, so that you have more opportunities to put things in different units. Usually in this kind of architectures, your branches have delay slots, which means that when you execute the branch instruction, it doesn't take the branch immediately, but you have a few cycles of delay. And if you fill these instructions if you fill the cycles with some instructions, then you can kind of reduce the cost of branching, which can be quite important for small loops. And finally, the last aspect I will present is you really don't want any dependencies between your instructions. You want to avoid them as much as possible. That's because if you have instructions that depend on another, you can't execute them in parallel, so you want to avoid them. One way to do this is to rename registers after register location. For example, there's a path in LLVM to do this. And you can also do early scheduling so that it will affect register location. So now let's look at what kind of pitfalls you can expect from this kind of architecture. Something important you have to know is that for VLIW architectures, scheduling is not just an optimization. You have to do scheduling in order to get correct code at all, otherwise your code will just crash and burn. I don't want that. So one reason for this is usually you don't have any instruction in interlocking as a pipeline level. So it means if you have dependencies between instructions and the processor don't wait for you to satisfy the delays between the instructions. That's to reduce power consumptions. So that's why the compiler, or in this case the scheduler, has to know about these dependencies and the latencies, and in order to avoid these conflicts. So we'll present two common kind of hazards that you have to handle. The first one we can call operand not ready, or it's really like read after write hazard. So if you have two instructions, one instruction has maybe quite high latency that reads the value, and the second instruction that consumes the value, you have to make sure that the result is ready by the time you want to use it. Otherwise, you'll just get the previous value from your registers. So that's why the scheduler has to enforce the kind of delays between instructions. And the second kind of really common hazard is to do with register ports. So with this architecture, if you want to read values from register, if you want to write values to registers, you have to use ports to the register file. And different functional units will share the same ports, so potentially you can use the same ports at the same time, like in the same cycle. And if you do this, you'll get the wrong result, like one of the two values will be written. And so that's why your scheduler has to track these conflicts and make sure that instructions don't use the same ports at the same time. So that's for the most common hazard. Obviously, there are others, but they are the most important ones. So let's look at what the scheduler produces. So here we have a cycle table where the columns are all the functional units, well actually almost all of the units, and the rows are simply cycles. And inside the table we have the instruction we want to execute. So you can see if for a given line, if you have multiple instructions, that it means they happen in parallel. So basically, the goal of the scheduler is to pack this table as tightly as possible so that you have maximum ILP and hopefully minimum execution time. But, well, as we'll see, it's not always easy. But now let's see how we can implement this within LLVM. So here you can see the different scheduling passes we use as a kind of like high-level overview. So we have two of them: early scheduling just before register location, and late scheduling before emitting machine code. And as I have mentioned earlier, we do anti-dependency breaking to rename registers and potentially avoid dependencies. So most of the work for scheduling, as you can expect, is in the scheduler. So the scheduler uses a quite common scheduling algorithm, list scheduling, so I don't think I have to introduce it here. One thing the scheduler has to do is to enforce the dependencies between instructions. You don't have this read afterwards hazards. In order to do this, it has to know about scheduling information from the target, so that for instructions, which operands are used, which ports are used, which each operand, the latency, and so on. And something else that the scheduler does is to take multiple instructions and try to pack them into a given cycle in a bundle to maximize the ILP. In order to do this, you can move instruction from one unit to another, and but you need to know if that's safe or not to do. So you need something called the hazard recognizer. So the hazard recognizer is basically there to answer queries from the scheduler, and the scheduler wants to know whether it can schedule two instructions in the same cycle. And in order to do that, this hazard recognizer will need to keep track of which instructions have already been scheduled. And to do this, it's used what's called a scoreboard approach, where it builds a kind of cycle table that we've seen before. But we not only track which functional units are used, we also track which ports are used, and so on. And the idea is that of all of these resources, like ports or functional units, two instructions can't use the same resource at the same time. And so that's why the hazard recognizer can say, well, no, you can't execute these two instructions at the same time. So something we want to do is to move instruction between units. And something we've observed is that units have overlapping functionality, like they have common instructions, effectively. For example, if you look at the load store unit, you have two of them, and they are basically the same, except they use different ports. So you want to move, for example, memory operations from one unit to another. And so here, let's look at an example. So this is kind of a cycle table we've seen before, and here we have two memory operations, and there is no dependencies between the two. And we see here this load store unit is free, so we ideally want to take this instruction here and move it there. And if we do this, we only take one cycle instead of two, so potentially we get faster code. So to do this, we just take our instruction and move it to the other unit, and then we have to make sure that it's actually beneficial. So we can calculate a new cost, and if the cost is worse than before, we just revert the changes, otherwise we keep this instruction. Right, so let's see what kind of result you can expect if you implement these three optimizations for a VLIW target. So we've used the TSVC benchmark to do this, and this benchmark was originally designed to exercise the vectorization in a compiler to see if it's able to vectorize a lot of different kind of loops. So that's why each test is a loop. And these loops are grouped into different categories where each category is a kind of pattern that you want to vectorize. So we are going to show for each category how many cycles it takes to execute all these tests. And we're going to show this for different optimization, like the baseline and so on. But we have not done any analysis of per categories tests. And the reason why we're showing these results at all is because we want to show that if you have an optimization, it has different results, different impact depending on what kind of code pattern you run on. So the first optimization that you really want to do is partial loop unrolling. So this is already present in LLVM, but for some reason it's not enabled by default. So you really want to pass these options to LLVM. And in order to use it, you need to cross model, as Erkan explained before. And basically, well, I'm sure you know what loop unrolling does. Just expands a loop body into multiple copies, and then what this does for VLIW architecture is introduce some opportunities to move things around and hopefully fill the units better. So you can see this is quite gives us quite important speed up from I think 33,000 cycles to just under 20,000. And as I've said, it's already in LLVM, so I just pass the options and you'll get a lot of benefits for pretty much no work. The second one you want to do is to fill the delay slots. So in this architecture, we have 6 delay slots, and without the optimizations, we have to fill these slots with knobs, so it's quite wasteful. It's especially wasteful for loops because you pay these costs, these 6 cycles, for every iteration of the loop. So any reduction will give you a really nice speed up. So if you fill the slots doing some bottom-up scheduling, then you will greatly reduce the cost of branching for small loops. That's why you can see that we have quite nice speed up here, and you can imagine these loops are quite small. And finally, the last one we're going to present today is you want to use the same scheduler before and after restore location. The reason for this is when you do this, you will cluster higher latency instruction like loads, and then the live variables, the live ranges, so you have the variable will be overlapping, and the restore locator will have to allocate different registers, which breaks the dependencies and prevents these dependencies and give you better code in the end. That's why it works well with loop unrolling, because if you have more code, then you can avoid the dependencies and have better ILP. So you can see the speed up is not as important, but we still think it's quite good to have it. So let's look at the overall results. We're around 34,000 cycles here as baseline. And with these 3 optimizations, we get to around 11,000 cycles, I think. So the biggest gain was simply to enable this partial loop unrolling that's already present in LLVM that gives us 1.8 times speed up. This branchless slot filling optimization we've implemented gives us around 1.6x. And finally, using the same scheduler before and after scheduling, 1.1 time speed up. And overall, 3 times speed up for this only 3 optimizations. So we think these 3 are quite important to implement in this kind of architecture to get good results. And this concludes our talk. So thanks for attending, and if you have any questions.
Yeah, I was interested in how much of the standard LLVM infrastructure you used and how much was kind of custom added to represent the process.
Right, so we used most of the, this is through Clang. So we've taken C and C++ code and then we compile it to IR and then feed to the backend. So we use most of the custom passes. And we do have some custom passes optimizations, but it's mostly like code generation. It's not, we don't have anything that's kind of like higher level. We don't have any like loop optimization or something.
So things like the scoreboarding and the hazard recognizer and the bundling and that kind of
Yeah,
stuff.
so this is specific for the target.
Okay.
Yeah, because for example, for the hazard recognizer, we need a lot of states. So I think there is a scoreboard hazard recognizer in LLVM, but it only tracks the function units. And we have to track the ports, we have to track a lot of things. And when it comes to bundling, we do both scheduling and bundling at the same time because it's quite neat with Shape. You just have a table, you just pack your instructions. It doesn't make sense to do two passes, if it makes sense. There was a question here.
My question was mostly when this is going to actually arrive upstream. I know that there was an email discussion that started.
Right. So
yeah, we don't know. Yeah. Actually, yeah, this work is done for the movie videos, so they know. Yeah, better. Yeah.
Right. So I'm from Codeplay, and we've been working with Movies to implement some optimization in their backend. But the decision to upstream this is there. So we've also seen this email, and we hope this will happen quite soon because I think it's quite cool architecture to play with, and I think it would be good to have another kind of VLIW target in the backend. So yeah. Any other question? Yeah.
You said with this architecture, you have you need to wait for the value to be ready. So are the latencies for producing the value guaranteed?
Yes, they are fixed. So I think.
So you can be absolutely sure that it will be there.
Yeah. So it's completely static. You know exactly when things happen. So it's really neat. That's why we have this table. You know exactly, like if you have this. I don't have in rows here, but let's imagine this takes 5 cycles. You exactly know that your result will be available here, so that you can. And I think the reason for this is that this is used in embedded settings where you don't have an OS on it. You just have like a set of programs you control, so you know everything, and you can optimize, like do profile guided optimization and save power with because you don't need all these things like speculative execution and out of order. So it's an in order core. Yeah, I originally planned for a half an hour talk, but we only have 15 minutes, so I had to remove a lot of details about the architecture and so on. Yes?
So just a quick one. So you mentioned that delayed slot filling helped quite a lot. 6 is a lot of delay slots.
Right.
How filled did you get it?
Well, it depends, but quite often we were filling completely. Depends on the code, but if there are no not too many dependencies, you can.
Right.
For example, here a good example. While we are filling, all of them here, we have this 2, 6, 7. So basically, we have to.
Such a lot of delay slots.
Yeah. Yeah, and you have to fill them for potentially for all the units, but you never do that because it's too many instructions. And yeah, so yeah, the problem is that even if you manage to kind of optimize this better, you're still limited by this 6 slots. You can't shrink the loop any further because, for example, here you increment your injection variable and then you compare it with.
Yeah, I was more worried about having to fill a lot of nums and it just
yeah.
like, it's gonna be too much of an issue.
Yeah, it completely depends on the code you have, and yeah, that's before loop unrolling. So if you do loop unrolling, you see a lot better utilization of the units. And yeah.
For the anti-dependency breaking, so you use the scavenger to rename that?
Sorry?
For the anti-breaking dependence,
yeah.
You use the scavenger to, how did you do to find new names in the register?
This is done by LLVM, not really sure the details. The only time I had to work with it.
You didn't extend it, nothing to be extended?
No, we found a couple of bugs and we tried to work on them. Unfortunately, we used when I was working on it, we used a quite late old version of LLVM, so it was difficult to pull this code back upstream. But hopefully, when the process of merging this back to LLVM happens, then we can just remove all of this workaround and so on.
You can find the bug.
Sorry?
You can find the bugs.
Yeah, we should do that. Yeah, unfortunately, I don't work for this project anymore, but yeah. Any other questions? Yeah.
Can you go back to the slides with early and later stages?
That's this one.
Yeah, I was wondering, because you are doing early scheduling before the register allocation, did you try out that algorithm on some non-orthogonal, very long instruction platform that would be actually best benefit for?
So can you repeat about
orthogonal? Did you try any of the non-orthogonal platforms, very long instructional platforms, where this basically you would kind of maybe suggest to allocator how to allocate things so you can better schedule it later? Because those kind of platforms kind of depend on the allocations, so depending what you can actually schedule later.
So, do you mean running this same kind of code on different targets?
Yeah.
Yeah. No, we only focus on this.
Only for that. Okay.
Yeah. But the interesting thing is that we were using, before using this chef scheduler here, we were using the LLVM one, the machine MI scheduler, which is a bit more advanced than what we use. And actually using the same one before and after was much of a boost because it's, well, as I said, it overlaps the live ranges and forces the register allocator to allocate different registers. So we tried to use the ILP scheduler, and it was doing the completely opposite that we wanted. It was doing, for example, like load, multiply, store, and the register allocator would say, well, okay, the live ranges are quite small, I just reuse the same register, and then after register allocation, you want to do scheduling, and like, well, you have so many dependencies, you can't parallelize anything, and so that's quite, we're quite surprised that using a maybe not as featureful scheduler gave us some improvements because of register allocation.
The VLIW scheduler, at least, the STAG scheduler is due to be removed, I think, at this point. So, you know, if you want it, you might want to think about that.
Yeah, we can do some more experimentation. And, what we tried to avoid was writing a new register allocator for our needs. So I think it was just much easier to use the same scheduler before register allocation than writing a new allocator.
Yeah, I'm curious what was going on with the ILP scheduler.
Yeah.
So I have a theory. I think that the ILP scheduler is essentially trying to build ILP for registry naming targets.
Right.
And it doesn't have the appropriate hooks for targets where register dependencies actually block ILP as a hard block.
Right.
And so I think we just need a separate scheduler which is specifically avoiding dependencies.
No, that's probably true, because what it's trying to do is largely use as many registers as possible, finalize as many things to get as many back, and then rinse and repeat.
Yeah, I think we just need a scheduler that's actually really targeting VLIW style architectures that don't have registry naming and need the dependencies to be broken.
We could probably make the VLIW scheduler that, to be honest.
So
Did you implement an assembler for this architecture as well? Do you have an assembler for this architecture?
Yes.
So I guess that do you have to write a canonical assembler input, or it's lax and you do all the hazard checking and slot filling?
I think historically the assembler has done some of this scheduling and hazard checking, but now it's done the pilot. So you have C++ code that you complete plan that generates your assembly, and then you just the assembler just take the assembly and doesn't do any processing. Yeah, doesn't do